Hey guys, and welcome back. Today we are talking about net forces. So we've talked about how to calculate force. So we know that force is mass times acceleration, which we'll be reviewing a little bit today. But we're also going to talk about something called force diagrams, and I'm going to show you how to draw those today. So let's go ahead and get started. So just a quick review of Newton's second law. When we're calculating force, we use this equation. So force is equal to mass times acceleration. So F is going to be the force in newtons, M will be the mass in kilograms, and then A is the acceleration in meters per second squared. Remember, that is our unit for acceleration. So let's go ahead and take a look and just remind ourselves of frictional forces. We talked about this a little bit in yesterday's lesson as well, but just a quick review. Friction is the force that opposes motion. So like here we have this guy, he's trying to slide across the floor, but there's friction as he moves himself across the floor, making it more difficult for him to slide along. So it's the force that opposes your motion. It's the friction that's happening between you and the contact with the floor. So sliding friction opposes the motion of two surfaces as they slide against each other. So this guy right here in this image, there's friction between him and the surface of the floor that he's trying to push himself across. Static friction prevents two surfaces from sliding against each other at all. So everything has static friction, it prevents movement. And then rolling friction is static friction that keeps a wheel from spinning in place and makes it turn instead. So if you think about tires on a car, because there's rolling friction, that actually allows cars to be propelled forward instead of that tire just spinning in place on the car itself. And then air resistance is the force that opposes the motion of objects that move through the air. And this, of course, is going to depend on an object's size, shape, and speed. So remember, if you think about people who jump out of planes, maybe go parachuting for fun, when they open that parachute, they have an increased surface area, which increases their overall wind resistance, which allows them to slow down and reach the ground safely. Okay, so air resistance can be important when we're talking about forces and things that oppose movement. So now let's talk about net force. So net force, or the resultant force on an object, is the sum of all the forces on an object, okay? Because when you have an object, there's going to be forces working on it from multiple different directions, okay? So in this example, this is a force diagram, and we're going to talk about these a little bit more today. But with this force diagram, you basically have the object. A lot of times it's represented by a box. So you just draw a box on like a plane or a tabletop. So this would be representing a tabletop right here, this horizontal line. And you basically draw arrows in the directions that forces are working on the object. So in this case, it's a physics textbook. So we have an arrow that's drawn down to represent the force of gravity. Okay, so this downward arrow represents that there's a force of gravity that's working on the physics textbook in the downward direction, okay? And in this particular instance, that force is 20 newtons, okay? Remember, force is equal to mass times acceleration, so it depends on the mass of the physics textbook, okay? At the same time, the table is pushing on an upwards motion with a force of also 20 newtons. When an object is at rest, so when you are at rest or an object is at rest, the force of gravity and the force of the upward motion are equal, okay? So if you can see 20 newtons and 20 newtons, if an object is stationary, those forces cancel out, okay? So we don't have to worry about those. However, there is a frictional force that's pushing leftwards with 5 newtons. Okay, so we're pushing in leftward in the left direction 5 newtons, and that's that frictional force. Remember that force between the table and the textbook. Now the 20 newtons up and the 20 newtons down are going to cancel each other out. So the net force of this particular instance is going to be 5 newtons. Okay, so the total net force here is 5 newtons because our gravity and our upwards forces cancel each other and just leave us with that 5 newtons of frictional force. So again, with the force diagram, the lines of length represent the size of a force. So typically when you're drawing these, the larger the force, the longer the line. The arrows are going to point in the force direction, and then the labels represent the type. So for example, here we have the force of gravity, which always works downward. The opposing force that opposes the force of gravity is known as the normal force. Okay, so the upward area is going to be the normal force. Typically, in every single force diagram you do, you'll have the force of gravity and the normal force. And then here you have your force of friction, and you have your applied force as well. Now, an applied force could be like you pushing the textbook or the object across the table. Just depends on what the problem tells us, okay? And then here's an example. Again, it doesn't matter what it is. It can be drawn and represented by just a square box. So this square could represent like a person or an elephant or anything at all. Okay. And again, we can find net force from a force diagram. So here's an example. Again, we have the assumed force of gravity and the normal force, which are equal and opposite to each other. So really, we're just looking at the frictional and the applied forces here. So on the left-hand side, we have a force of 10 plus 8, so that's 18 newtons going in the rightward direction. And on the left-hand side, we have 5 newtons and 2, so that's 7. So 7 newtons in the leftward direction. So we have 18 newtons towards the right, 7 newtons towards the left. So the overall force is going to be moving this object in a rightward direction because the force of the applied force on the left-hand side is higher than the applied force on the right-hand side. So the total net force here would be 18 minus 7, which is just 11. So 11 newtons would be the total net force here. So also when we're taking a look at these objects, exerting a bigger force on an object will cause a bigger change in velocity as well. So an object with a bigger mass will have a smaller change in velocity. And you can think about that if you have, one textbook on the table versus an entire stack of textbook. The stack that has the greater mass is going to take more force and be harder to move than the one single textbook. So it makes sense that those objects that are larger, it's going to take more of a force to move them, and therefore they will have a smaller change in acceleration. So for example, here we've got 2 different boxes. One has a mass of 2 kilograms and one has a mass of 3 kilograms. They both have an applied force of 12 newtons, but the acceleration of the 2 kilogram box is 6 meters per second squared versus 4 meters per second squared in the case of the larger box. Okay, so we're going to see a higher acceleration on the object with the lower mass. And these are just some more examples of force calculation. So again, this is Newton's second law. Force is equal to mass times acceleration. So these are up here for you to take a look at. You can pause and work through these. I'm not going to go over these right now just because we've done this for 2 days now. So we've done force calculations in both of your lessons, but this is an extra example that you can work through, pause the screen, and take yourself through just in case you need some extra practice. Now today you will be drawing force diagrams in your assignment. As always, please watch the video before you try the assignment where I go over some problems with you, and then that way that can kind of eliminate any kind of confusion we might have. Okay? If you have any questions, let me know. And if not, I will see you guys in your assignment video for today.